In this lecture, we will examine PLC size and application. The criteria used in categorizing PLCs include functionality, number of inputs and outputs, cost, and physical size. Of these, the I/O count is the most important factor. The criteria for categorizing PLCs include functionality, the number of inputs and outputs, cost, and physical size. Nano PLCs are the smallest, with fewer than 15 I/O points. Micro PLCs expand this to between 15 and 128 I/O points. Medium-sized PLCs range from 128 to 512 I/O points. Finally, large PLCs are capable of handling over 512 I/O points, making them suitable for large and complex industrial systems. A single-ended application means that one PLC is dedicated to controlling one process. For example, in this diagram, a single PLC controls the cutting operation by receiving sensor feedback, monitoring stock position, and controlling the motor and cutter through the operator interface. It's a simple, direct relationship between the PLC and one specific process. In a multitask application, one PLC is responsible for controlling several processes at the same time. Here we see an example of an engine assembly line. The PLC handles multiple steps, from machine assembly to hand assembly, adjustments, and quality checks, all with one controller. This shows the flexibility of PLCs in managing multiple operations simultaneously. A control management application involves one PLC supervising several other PLCs. In this setup, the main PLC coordinates the activities of multiple subordinate PLCs, each handling different processes. This hierarchical structure allows for distributed control, greater scalability, and easier troubleshooting in large systems. Memory is the part of the PLC that stores data, instructions, and the control program. Memory size is typically expressed in K values such as 1K, 6K, or 12K. Unlike the normal definition of kilo as 1,000, in computing and PLCs, 1K equals 1024 because of the binary number system. Depending on the memory type, 1K can represent 1024 bits, 1024 bytes, or 1024 words. The amount of memory required depends on several factors. These include the number of I/O points, the size of the control program, and any data collection requirements. Supervisory functions and the potential for future expansion also play a role. For example, a Micrologic's 1000 controller may only need 1K of memory for up to 20 inputs and 14 outputs, while a ControlLogic's controller may require up to 32 M to handle as many as 128,000 I/O points. The instruction set of a PLC defines the specific commands and functions that the controller is capable of executing. In other words, it is the vocabulary that the PLC understands. Just like a spoken language relies on words to build sentences, a PLC program relies on instructions to build logic. One of the most common instructions is examine on, or XIC. This instruction checks if a bit or condition is true before allowing current to flow through that part of the logic. It is often used to represent normally open contacts. Next is examine off, or XIO, which does the opposite. It checks if a bit is false before passing logic through. This is typically used to represent normally closed contacts. Together, XIC and XIO form the foundation for decision-making in ladder logic. Another key instruction is output energize, or OTE. This instruction is used to turn an output device, such as a motor starter coil or an indicator light on, when the logic leading to it is true. Without OTE, the PLC would only be monitoring inputs, but never controlling anything. In addition to these basic instructions, PLCs also include memory-based instructions such as latch, OTL, and unlatch, OTU. A latch instruction is used when you want an output to remain energized even after the condition that triggered it goes away. The unlatch instruction removes that condition when a separate logic path tells it to reset. These are very useful in processes where you need outputs to hold their state until specifically reset, such as alarms or machine start/stop sequences. PLCs also support timers, such as timer on delay, TON, and timer off delay, TOF. This instruction turns an output on after a preset delay once the enabling condition is true. For example, it could be used to start a conveyor belt 5 seconds after a sensor detects a part. On the other hand, TOF instructions keep an output on for a specified time after the enabling condition goes false, such as keeping a fan running to cool equipment after a machine shuts down. Finally, there are counters, such as count up, CTU, and count down, CTD. Counters allow the PLC to keep track of how many times an event occurs. CTU counters might be used to count how many bottles have passed on a conveyor line, while a CTD could be used in applications where items are removed from an inventory or a batch count needs to be reduced step by step. These instructions may look simple individually, but when combined, they become the building blocks of very complex and powerful control systems. With them, engineers can design programs that automate entire manufacturing processes, ensure safety interlocks, perform quality checks, and optimize production efficiency.